This is Dr. Carroll, and this video is about Huffman Codes. Now, Huffman Codes are a great example of greedy algorithms. And the point of Huffman Codes is to achieve file compression. So the ASCII codes has approximately 100 printable characters and a handful of non-printable characters. And so each character requires 7 bits of information. Because that's log base 2 of 128 is the total there. And then there's an 8th bit for parity. So it takes 1 byte to store an ASCII character. For example, the ASCII character value 7 is a beep. That's an example of a non-printable character. Try printing it sometime. Tick \B, untick, okay? So the way Huffman codes work is to assign the frequent characters the shortest codes, and you can reduce the number of bits required and hence the file compression. This can generally save about 25% of storage space for large files and 50 to 60% for some large files. Okay, so let's see an example to see how this works. Let's assume that we had the following letters, a subset, and just again, it's a simplified set so we can see it. The following letters here, A, E, I, O, U, Y, and exclamation mark, with the following frequencies, okay? Yes, I know you're very limited in the words you can spell with those, but for example, okay? And so then, because we only have these 7 numbers here, we can encode them with just 3 bits. We could arbitrarily assign them in order 000, 001, etc. And we could encode all of them faithfully. Now, if we did this, we'd have the following total bits. And this is just the frequency times by the number of bits here. So for A, we'd have 60. For E, we'd have 90. And so what we'd really like to do is reduce the ones that have a higher frequency. If we can give them a smaller code, that will reduce the total number of bits needed to store it. Okay, so here in this example, we have 115 characters in this file, and therefore requiring 345 bits. Now, characters with Huffman codes are only going to be stored at the leaves, only at the leaves of this tree that we're going to build. And when we traverse the tree, if we traverse it to the left, we're going to append a 0 prefix to that letter. And when we traverse it to the right, we're going to append a 1 to the prefix. So let's see an example that illustrates, let's see the tree that illustrates this example. Here we have it, A, E, I, O, U, Y, and exclamation mark. Now, as I mentioned, if you traverse left, you append a 0 to the code, left. So as I mentioned, A is 0, 0, 0, and E is 1, 0, 0, 1, and so on. And that's how we get each of these letters in the Huffman codes for it. Now we can improve a little bit upon this, and that you notice there's no right child here. So if we have a 1, 1, we already know that it's going to be an exclamation mark because there's no right child. So what we could do is just actually move this one up, which is going to reduce the number of bits needed. In this case, not very much because exclamation mark was infrequent. Okay, and so then if we had the encoded string 0000100, etc., that would be decoded into A, because we would notice we'd just follow our pattern 000. Okay, well that has to be A, and then the next 1, well 1 doesn't uniquely define anything, so 10, that doesn't uniquely define anything, so 101, 101, that's a Y. We start over, well, 1 doesn't uniquely define anything, so 10, no, 100, and then we have U, and then we have 000A, 000A, and then we get U and A. So that's how this is encoded. But we haven't saved anything yet. So this is the normal case that we're trying to beat. This is pretty much how your well, like this video text file actually is stored, something very analogous to this. It's all stored and we know exactly how to read it. Okay? But so now what we're trying to do is we're trying to compress the file and save some bits. So Huffman, a couple years ago, presented the following greedy algorithm to get the optimal solution. First, assign each character to a node and thereby making it a tree, okay? And then we'll assign the frequency of that character as a weight, and we're going to work with the trees based on their weights. Step 2 then is to combine two trees with the smallest weights as children into a new tree and assign the weight of the sum of the children as the weight of its tree. And you probably guessed it, step 3 is repeat step 2 until all the trees are combined. Okay, well, let's see an example. So here we have the same set of letters, except I've sorted them so that they're in the order of least frequent, because that's how we're going to combine them. So step 1 was make all the nodes and assign weights. Check, we're done, okay? Now step 2 was combine the smallest two trees into children of a new tree. Okay, well, that's going to be these two, and all of these are trees. And we'll label the new tree T1, and then we've updated its height to be 7 because there's 1 plus 6. And these numbers, remember, are the frequency of the letters. So E is the most frequent, and so we want to have the shortest code for it. And then step 3 was repeat. Okay, let's see the smallest two subtrees, smallest two trees. That'd be this one with 7 and this one with 8. We combine them, update it to 15. Smallest two is going to be 15 and 20. Okay, smallest two, it's 24 and 26 here, so we'll combine them to get 50 here. Now smallest two would be 30 and 35, so we'll combine them, then we'll smallest two, and then we're done. We've combined them all. Now to get the Huffman codes, all we need to do again is apply the 0 for the left child and the right for the 1 for the right child. And then if we follow this, for example, exclamation mark, we determine is 0, 0, 0, 0, 0. And then Y would be 0, 0, 0, 0, 1, and all the letters accordingly. So notice that E has a very short code, 0, 1, and it's the most frequent. So we've reduced the amount of codes needed for E by 1, but it was the most frequent, so that was a big gain. We've also reduced it for I and O at the same time, so that was a big gain. Let's see how that works out, okay? We build this table again with our frequencies, our letters, and their codes. So then we have 1, if we're starting from the right, we're going to, O was 1, 1 is its code, and I is 1, 0, and then E is 0, 1, 0, 1, and then 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, and 0, 0, 0, 0. Maybe I had too many there. But again, we're going to calculate the total bits as the frequency times the number of bits needed, frequency times the number of bits, frequency times the number of bits, frequency times the number of bits. And then the real question is, did we reduce the total? And we did. 287 down from 345. And that's Huffman codes, an example of a greedy algorithm as it looks for the smallest weight trees, combines those, combine those, to be able to get the optimal tree in this case. That's it for this video.